Welcome to the 12th episode of our series, The Mother Earth. In episode 11, we learnt that the Earth, in its initial planetary history, should have had an atmosphere similar in composition to that of Venus. The composition of the atmosphere changed gradually as the Earth cooled and the primeval crustal blocks floated over the fluid protomantle around 4 billion years ago. The time span from 4 to 3 billion years was tumultuous on Earth. It was riddled by incessant meteoritic impacts, frequent volcanic eruptions, and speedy tectonic movements compared to the happenings in its later history. Though most meteorites impacting the Earth's surface traveled from the asteroid belt, some originated also from the Martian crust, which was in similar turmoil. The widely spread volcanic eruptions on Mars belong to that time span. The Martian volcano Olympus Mons is so far the largest volcano known on terrestrial planets. But the volcanic eruptions on Mars almost stopped in the first 500 million years ago, in its early history. This conclusion is published in the NASA report on September 2021. Hence, later inputs of volatiles to the atmosphere have been rather meager. In contrast, volcanic activity continues on Earth even at present. The most recent and very powerful being the eruption in Tonga Islands in the Pacific Ocean, which occurred on the 14th January 2022. The Hunga Tonga spewed up volatiles, chiefly the greenhouse gases carbon dioxide, water vapor, sulfur dioxide, methane, and ammonia high up into the atmosphere, rising about 50 kilometers above the Earth's surface, almost half the thickness of the atmosphere on Earth. The gaseous emanations spread out swiftly into the atmosphere. You know that many oceanic islands, like the Hawaiian Islands or the Iceland, have active volcanoes and are formed by expulsion and accumulation of lavas on the present ocean crust. Such volcanic activity was more frequent in the Archean Era, which is the oldest time span recognized in the Earth's geological history, from 3.8 to 2.5 billion years ago. Metamorphosed sedimentary formations of that age, that is the Archean Era, including the banded iron formations, are often thinly interbedded with chert, that is the cryptocrystalline silica, and with volcanic rocks like basalts. Such Archean sedimentary formations show no apparent signs of the presence of any form of primitive life, but it is believed that by about 2.7 to 2.8 billion years ago, some kind of bacterial life stepped into the atmosphere ocean crust system. It is believed that the appearance of the bacterial life helped in consuming the atmospheric carbon dioxide and in oxygenating the then oceans and the atmosphere. Laden with carbon dioxide, the atmosphere was similar on every terrestrial planet. How did its composition change on Earth and could not be accomplished on any other planet? On Earth, it began changing to carbon dioxide poor, nitrogen rich, and fairly oxygenated atmosphere about 2.5 billion years ago. Lavas erupting from fumaroles on ocean floors perhaps added elements like iron, nickel, chromium, along with copper, lead, sulfur, and phosphorus to the ancient oceans as well, together with gaseous emanations and water vapor to the ancient atmosphere. For volcanic eruptions on the present ocean floor, which is about 200 million years old, and the volcanic rocks associated with sedimentary formations that are deposited peripheral to the continental blocks, a linkage has been established with the convection currents within the Earth's hot fluid layer in its upper mantle. That such a layer is in fluid state despite its higher density than the crustal blocks has been established by seismic profiling. This fluid layer in the upper mantle is referred to as the low velocity zone or the LVZ by seismologists. We learnt in an earlier episode about the formation of the Earth's outer core at a depth of 2,900 kilometers from its surface. The heat gradient established in a short time after 4.55 billion years ago has supported the convection currents in its outer core till present. The LVZ at temperatures reaching more than 1000 degrees centigrade also came into existence in the upper mantle when the heat gradient got established in the Earth's crust and the mantle. Under the heat gradient setup, metamorphosed rocks in the deep continental crust, say deeper than 35 kilometers from the surface, produced silicate melts referred to as magma. The convection currents in the fluid layer of the upper mantle have been so important since they fostered the lateral and vertical movements of the entire crust and a part of the upper mantle, together referred to as the lithosphere. They have supported the volcanic and tectonic activity that resulted in compressed, rifted, and fractured rock formations vulnerable to the interaction with the atmosphere. If you recall, the protective magnetosphere around the Earth was generated by the convection currents in the Earth's outer core, isn't it? Most of the Martian atmosphere, as well as the atmospheres of Mercury and Moon, got scraped by the solar winds for want of such magnetosphere, apparently consequent to the waning of convection currents in their cores. Repeated pulses of compression and rifting, volcanic eruptions, thickened the continental crust. Lavas of rhyolite composition extruded, and plutonic rocks of tonalite, trondhjemite, granodiorite composition, referred to as the TTG group, intruded the crust repeatedly at different depths. The Earth's crust also acquired the high and lowland topography similar to that on the Moon. On Earth, the lowlands were the real ocean floors constituted of higher density basalts. The highlands were formed by the lighter and thicker continental crust, with feldspar quartz-dominated rocks in the upper layers, and the lower layers were formed by rocks with ferromagnesian mineral groups like the amphibole group, pyroxene and olivine group. This density difference was possible only because of the repeated intrusions of magma generated at different depths of the deeper continental crust. The deformation of the rock formations of the continental crust also contributed to the differences in altitudes, which caused mass wasting of weathered, loosened and fragmented rock debris down the slopes and gradients. Under the Earth's gravity, of course, similar to the rolling down of detached rock boulders down the slopes of the present-day mountains. The Earth held its atmosphere through this long period of turmoil above its solid crust. Of course, again because of its high gravity. It is assumed that the ancient atmosphere should have interacted with the Archean crust even more intensely than it reacts at present with the younger crust. We have learnt that very small portions of the Earth's ancient crust are left behind, called the cratons, as relics forming the inner regions of the continents. Geologists extrapolate the Archean atmosphere crust interaction by observing how the present atmosphere reacts with the crust. They follow the Huttonian principle. The present is the key to the past, referred to as the principle of uniformitarianism. That is what the Scottish chemist and naturalist James Hutton proposed in his book History of the Earth, published in the 18th century. It explains how the different geological features of the Earth's crust were formed by means of natural processes operating over the past billions of years. Almost 3 centuries prior, that is in the 15th century, the Italian scholar Leonardo da Vinci wondered how long has the river Arno eroded and transported the dissolved and suspended material in its water towards the sea. Some of the sediments were also deposited at the banks of the rivers. He asked himself further this question: how long have the lofty mountains provided the necessary gradient for the mass transfer on the Earth's surface? These questions, as you can see, inquired about the antiquity of the geological time and geological processes. The sedimentary geological record of rocks immediately younger than the Archean are grouped in the Proterozoic era, which began 2.5 billion years ago and ended around 600 million years ago. Obviously, the provenance for them were the weathered and fractured rock formations of the Archean era. Proterozoic sediments were deposited in lowlands peripheral or marginal to the continents. Yes, you guessed correctly. These time boundaries for the two systems of rock formations, Archean and Proterozoic, have been determined by finding ages of radioactive isotopes of elements constituting the minerals of their rock formations. Together, these two eras are referred to as the Precambrian Aeon. During that long time span, say from 3.8 billion years up to 600 million years ago, that is the initial more than 3 billion years, there dwelt no organisms possessing hard parts like shells or bones, which on burial could have left their fossil record. The Earth's surface cooled gradually during this long time span. The ancient atmosphere, laden with volcanic gases, also cooled. The cooling was sufficient enough for condensing the water vapor held in the atmosphere. It dissolved many other important constituents, especially the carbon dioxide, and huge volumes of such water precipitated. That resulted in slightly acidic rainfall containing chiefly H2CO3 and enhanced the mechanical and chemical weathering of the crust formed during the long Archean era. The diminishing level of the atmospheric carbon dioxide and its consumption in the long weathering process almost marked the advent of the Proterozoic era 2.5 billion years ago on the geological time scale. What have we learnt in this episode? We have learnt how the weathering of the Archean crust should have consumed and diminished the carbon dioxide levels of the ancient atmosphere of the Earth. How the fluid layer within the Earth's upper mantle should have supported the continued volcanism on Earth. How the convection currents in the LVZ should have fostered lateral and vertical movements, which deformed and fractured the Archean rock formations, rendering them vulnerable to the atmosphere-crust interaction. How the repeated volcanic eruptions on the Archean ocean floor and on the continental crust contributed to the dissolved elements in the then oceans. Following the Huttonian principle that the present is the key to the past, we could visualize the late Archean scenario, which perhaps provided the hospitable milieu for primitive life to step in and become stable as a part of the atmosphere crust ocean system. In the next episode, we will look into many other geological factors which contributed to the initiation of life in the late Proterozoic era. Thank you.